Good morning and welcome to my first video essay. So homeostasis is the state of steady internal physical and chemical conditions maintained by living systems. So homeostasis is basically, we're trying to keep everything steady inside the body. We're trying to keep pH level steady, temperature steady, and we have set points for all these things. And we're basically trying to stay at these set points. So now, some of the ways that we do this, that we maintain these steady internal conditions, are through reflex pathways. So our reflex pathways will often start with a stimulus. An example of this could be temperature. And this stimulus will take us away from our set point. And then we have receptors that detect this stimulus. So say we have receptors in the skin that detect a change in temperature. And then we're going to communicate with the control center, which is usually the brain, through afferent pathways. And these are usually either nerves or blood. And so we're going to communicate from our receptor to our brain through an afferent pathway. So you can think of an afferent pathway as the body is talking to the brain through nerves or blood. And then the control center, the brain, is going to interpret this message, and it's going to send a message back to the body via an efferent pathway, which once again would just be nerves or blood. And then this message is going to have instructions for the effector to take us back to our set point. So the effector in the case of temperature could be sweating. The brain might send a message to the body and tell it to start sweating, or maybe to start shivering if it's cold, for those muscles to produce heat again. So we go from our stimulus to our receptor to our control center via an afferent pathway, and then we go from our control center to our effector that fixes the problem and brings us back to the set point via an efferent pathway. So in homeostasis, we have a couple types of feedback loops. First one is called the negative feedback loop, where the variable is changed in a way that returns it to the set point. So an example of this would be temperature that I just went over there. So remember, very important with negative feedback, the variable is changed in a way that returns it back to the set point. Now, positive feedback is a response to the stimulus that results in a change to the variable that increases deviation from the set point. So positive feedback loops are often bad, but there are some cases in which it's good. So an example of a bad one would be we lose a lot of blood, and so in negative feedback, maybe we lose a lot of blood, and then we have a drop in blood pressure, and so our heart starts beating faster to increase our blood pressure and bring us back to that set point, the normal blood pressure. So that would be an example of negative feedback. An example of positive feedback would be basically our heart rate can't increase enough to raise our blood pressure, so our blood pressure continues to fall, and it takes us away from our set point. However, a positive example of positive feedback, an example where positive feedback is a good thing is in labor contractions. So in labor, the brain sends a signal via oxytocin to the uterus, which causes contractions. And then these contractions cause the fetus's head to press on the cervix, and then stretch receptors in the cervix send a message to the brain that tell the brain to release more oxytocin, which is going to once again take us back through this cycle until the baby is delivered. So that would be an example of positive feedback. So there's part one of the essay questions of homeostasis. Moving on to part two, we have our protein-mediated transport. So there's a couple different topics here in protein-mediated transport. So first off, it's going to be facilitated diffusion. So facilitated diffusion takes place through channels. And once again, diffusion is the movement of particles from a high concentration to a lower concentration. And so an example of simple diffusion would be just oxygen crossing over the cell membrane into the cell. It doesn't need any proteins in the membrane to transport that gas across the membrane. Oxygen just freely flows over the membrane from a higher concentration outside the cell, outside the body. Oxygen flows from that higher concentration to the lower concentration inside the cell. And it's simple diffusion. It doesn't need any proteins to facilitate that. But when we have solutes in the cell, maybe not gases, sometimes we need channels to facilitate this diffusion. When we have molecules or particles that are too big or too polar to just freely cross the membrane, we need a channel to facilitate that. So some examples of channels are voltage-gated channels, we have ligand-gated channels, and mechanically gated channels. So voltage-gated channels are sensitive to membrane voltage changes. So this membrane voltage is on the intracellular side of the cell. And based on what that voltage is, the channel, depending on the voltage, will open up and allow ions in. And with ligand-gated channels, oftentimes these are selective. So a specific signal molecule will come and bind to a channel, and then that specific signal molecule will open up the channel to allow particles to pass through the membrane. But ligand-gated channels require ligands, which are specific signal molecules. And then we have mechanically gated channels, which are sensitive to touch or pressure. So these channels will open up when they receive the stimulus of touch or pressure. Right? So that goes over our channels. And then for our carriers, you can think of these as a revolving door versus just an open door. So a carrier is not open to both sides simultaneously, right? So what'll happen is these carriers are specific to a certain type of particle or molecule or ion, and when that specific particle, molecule, or ion binds to the carrier protein, it causes a conformational shift, which then transports those particles to the other side of the membrane. So the particles bind from the extracellular side to the carrier protein, and that causes a conformational shift, which transports those particles to the other side of the membrane. So that is a carrier protein. And so a characteristic of carrier proteins, and this also applies to channels, is saturation. So both channels and carriers have a maximum rate at which they can transport. And saturation basically means that they get overwhelmed. There's too many particles to transport, and they can only transport so many at one time. So both of these types of transport are these are facilitated diffusion. They do not require energy. Now we're moving into active transport, which requires energy, usually in the form of ATP. And so active transport is going to move particles against their concentration gradients, right? Facilitated diffusion, right? We're moving with our concentration gradient, but maybe we're just too big or too polar to cross the membrane, so we need a little help. But with active transport, we are moving against the concentration gradient. And this requires energy to do that, just like bringing water from the ground floor to the top of a high-rise building. We're gonna require energy to do this. And so there's two types of active transport. We have primary active transport, and an example of this would be the sodium-potassium pump. And primary active transport uses ATP to pump solutes against their concentration gradient. So these pumps here have a binding site for ATP. We're specifically using ATP. So an example of the sodium-potassium ATPase, we're using ATP to pump sodium outside of the cell against its concentration gradient. Because remember, normally we have more potassium inside of the cell and more sodium outside. And so in order to move sodium outside of the cell and potassium into the cell, we have to use energy to go against that concentration gradient. So that would be primary active transport. And then secondary active transport is going to use energy from the concentration gradient established by primary active transport to move things against their concentration gradient. So, with secondary active transport, we are dependent on the primary active transport pump and its ATP working, right? And so oftentimes these secondary active transport will use a sodium gradient, right? So an example of this could be, we have a particle out here that has more concentration inside the cell than outside, but we're going to use this sodium concentration gradient to bring that particle across the membrane. So oftentimes a way you can think of this is sodium gets outside of the cell, and that natural concentration gradient, because there is more sodium outside than inside, that concentration gradient is going to bring the sodium into the cell. And so maybe some glucose gets swept up in that concentration gradient, and we move glucose across the cell membrane, or another particle that would be going against its concentration gradient here. But yeah, with secondary active transport, we are using energy from the concentration gradient established by primary active transport. And oftentimes this is done with sodium. And then just let me check real quick and make sure I covered all my bases with protein transport. All right, so moving on to osmosis. So osmosis is the movement of water from an area of low solute concentration to high solute concentration. So water goes where there are more solutes. So we have a couple terms here, osmolarity versus molarity. So the difference here is osmolarity refers to the number of particles per liter, and molarity refers to the number of moles per liter. So the reason we're not going to use molarity when it comes to talking about homeostasis and physiology is because substances behave differently when they're in solutions like water. So if we take NaCl, or salt for example, and we put it in water, it's going to dissociate. So we might have 1 molarity of NaCl, but then that's going to become about 1.8 osmolarity when it is in water, because those particles dissociate. So you could also say like, well, we have 1 molarity of NaCl, we have 1 mole per liter of NaCl, but we put it in water and it dissociates. So now we need to use osmolarity, referring to just the number of particles per liter in a solution. This is a better way to think about it in physiology, because these substances behave differently in solutions. So now we have osmolarity versus tonicity. So let's get our terms right. So we have hyper, iso, and hypo. Hyper means more than, iso is same, and hypo is less than. So if we have an isoosmotic solution, and I'm using 4 dots to represent 300 milliosmolar, which is basically the osmolarity of a cell. So here we have our beakers and cells separated. So a solution that is isoosmotic to the cell would have 300 milliosmolar of solutes in it. See, the cell and the beaker each have 4 dots. A hypoosmotic solution will have less solute than the cell. And a hyperosmotic solution would have more solute than the cell. So I put 6 dots in the hyperosmotic and just 2 in the hypoosmotic. So now we can have the same, well, let's go over tonicity now. So there's a couple different, so we have isoosmotic, hypoosmotic, and hyperosmotic, and we have isotonic, hypotonic, and hypertonic. So osmolarity refers to the amount of solute, right? The number of particles per liter in a solution. And tonicity is going to refer to the effect that the osmolarity has on the cell, right? So remember, water follows from an area of low solute concentration to high solute concentration. So in an isotonic solution, our cell is in our beaker. We have 300 milliosmolar outside and inside the cell. So there is an equal number of solutes inside and outside the cell. Therefore, this solution would be isotonic, and the effect on the cell would be that the tone of the cell would be normal. It's not going to swell or shrivel up. But in a hypotonic solution here, we have more solute inside the cell than outside. And so what does water do? It goes from an area of low solute concentration to high. Water goes to where there's a high solute concentration. So in a hypotonic solution, water is going to flow into the cell, and that cell could potentially burst. It's definitely, in a hypotonic solution, a cell is going to swell and possibly even burst. And in a hypertonic solution, we have more solute outside the cell than inside, so water is going to leave the cell to try and reach equilibrium, and our effect is going to be that our cell shrivels up. So a hypertonic effect is the cell shrivels, hypotonic is that the cell swells, and isotonic is that the tone stays the same there. Okay. Let me go back and make sure I covered all my bases when it comes to these questions. Okay, so now I need to discuss how a solution can be isoosmotic yet hypotonic, right? So we can have the same osmolarity and different tonicity based on how different solutes interact with the cell. So let's say that these dots here outside of the cell are glucose. So we know that glucose goes into the cell and gets metabolized. But maybe we have 300 milliosmolar of glucose. Maybe we have a 5% dextrose solution that's outside the cell in our beaker. And we have 300 milliosmolar inside the cell that is made up of proteins and other solutes in there. So what's going to happen is that glucose is going to cross the cell membrane and become metabolized by the cell. The cell is going to eat it up because it uses glucose for fuel. And so then we're left with, since the cell metabolized that glucose, the glucose crossed the cell membrane and got metabolized. Now the cell has more solute inside of it than outside of it. So thus, this is going to be a hypotonic solution now that the glucose is gone, and water is going to flow into the cell because osmosis dictates that water follows regions of higher solutes, right? So if we lose our glucose from the beaker because it gets metabolized by the cell, our osmolarity is no longer equal. So water is going to flow into the cell and make it swell up and burst, which is a hypertonic effect. Not hypertonic, hypotonic. So once again, same osmolarity, different tonicity. And this has to do with how different particles interact with the cell. So glucose, we might have the same osmolarity of glucose in a beaker as in the cell, but that cell's gonna eat up the glucose, and then water's gonna flow into the cell and have a hypotonic effect. So thank you very much for watching my video here, and I hope you have a great day.